Good morning. Can everybody hear me? Before I get started, can somebody let me know if you guys can hear me?
Yeah, I can hear you.
Okay, thank you. Um, does anyone have any questions about things in general before we get started on chapter 3?
When's our midterm?
Well, the midterm's available now. It has to be taken, oh gosh, I don't have the schedule in front of me. I think it's next Sunday, I believe. I believe chapter, if I remember correctly, chapter 3 and 4 are due this Sunday. And then I think chapter 5 is actually due on Friday night, and the final's due by next Sunday.
Okay, thank you.
So that would be date-wise. Let me share the screen really quick. I'm pretty sure that's right as far as what I was saying, but you can check the schedule. But everything is open, so you can do things as soon as you're ready to do them. So if you want to work ahead, you're welcome to work ahead. You want to take the test early, you're welcome to take the test early. So the 14th would be when the chapter 3 and 4 are due, which is what we're covering, this week in the Zoom classes. And then I believe chapter 5 is due on the 19th, which is Friday. And then that gives you a couple days. I wanted to make sure that the homework wasn't due the same day as the test, because then inevitably somebody would leave it till the same day as the test. And I want you to finish the homework and have a couple days to study. So chapter 5 is due on Friday the 19th, and then the test is by the 21st. And then after that, the final is due by the 7th of July. So, I mean, geez, we're less than 2 weeks into the class, and we have less than, we have 4 weeks left of the class. So it goes fast. It really does. Okay, so I'm going to pick up with chapter 3, and I didn't put the starting screen up, but the chapter name for this chapter is data description. And so we're going to be talking about how to describe a set of data. And the main topics, if you look at like each of the 4 sections in this chapter, there's actually there's 4, but we only do 3 of them. So there's measures of central tendency, measures of variation, and measures of position. So let me write that down. So there's central tendency. Too small, just a second. All right, so central tendency, which central tendency are like mean, median, mode. What could we say as far as like where the center of the data is? If you have a big group of data and you had to say, it centers around this, what would you say? Well, there's different ways to look at that. And in general, that's called central tendency. And then variation, like it says here, variation and position. Those are the 3 sections that we're going to talk about in chapter 3. So measures of central tendency, measures of variation, and measures of position. So variation, this means how much is the data scattered. So is the data scattered out, or is it all kind of clumped together? Is most of it clumped together, but there's one thing, a couple values that are far away? So that's what variation kind of addresses. And then position looks at where a single data value is in relationship to the others. So position would be things like your percentile rank, or your, there's also quartile. So percentiles, when you split it up into hundreds and you say, where would you fall if this was the data for 100 people? Quartile would talk about, are you in the bottom quarter, the next quarter, the upper, you know, next three, you know, the next quarter, like from 50 to 75%, or are you in the tops quarter? So the quartile splits it up into just 4 groups. You know, are you in the bottom 25%, the next 25% from 25 to 50, in the group from 50 to 75, or are you in the top from 75 to 100? That's the quartile. Whereas percentile, you guys are all probably intimately familiar with percentile ranks between, you know, your class rankings and your test results that you get back and things like that, your standardized test. It always, a lot of times it'll tell you what your percentile rank is. So if there was 100 students that took this test, where would you have fall? Would you fall at the 52nd percentile, the 82nd percentile? Where would you fall within a group of typical 100 people? So anyway, but that's not until section 3.3. So in traditional statistics, the central tendency is often denoted by the average. And I think we talked just a little bit last week that the word average, we think it means mean. Like that's what you're told when you're in younger grades and, you know, lower math classes. You're told that an average is the mean. An average is actually what we call the what you were taught was actually called the arithmetic mean, or the arithmetic average. So the mean and the average are what you used to know. That's where you add them all up and divide by how many there are. You've done that for ages. The median is the middle number in a set of data, and we're going to do all of these, but the median is the middle number. The mode is the one that occurs the most often. And then there's what's known as a mid-range, and then you can do a weighted mean if you have like a grade point average is a weighted mean. The way this class is graded is a weighted mean when we have like each of the parts are worth a certain amount. So the fact that, you know, when we have the 30% for homework, and then 35% for the midterm, and then 35% for the final, that's a weighted grade. And so when your final grade is calculated, it's a weighted mean. So you take your homework and you count that as 30%. It's not based on just points like some classes may be. You'll find weighted means a lot more in math classes where the teachers understand what a weighted mean is. You'll find point systems a lot of times in like an English class or history class, because the teachers a lot of times don't like the math as much and just want to base it on a real simple point system. So I found that to be quite true, that you'll see the weighted means more in science and math classes, and you'll see the point systems used in more of the humanities and that type of thing. So does anybody have any general questions before we get going with the specifics? Okay, so here we go. So when we're looking at measures of central tendency, there's 2 different things that we talk about. A statistic is a characteristic or measure obtained by using the data values from a sample. So when we talk about, I mean, that's what our class is called, statistics, right? So we're trying to figure out in a statistics class, we're trying to figure out the measurements for a sample. And you may not have realized that. You may think, oh, statistics is about figuring out things about populations. Yes, we use statistics to predict things about a population, but the statistics are actually from the sample. If you're talking about the population, we actually call that a parameter, and you don't hear that nearly as much. So they'll say the statistics show. Well, when they say the statistics show, they mean the data that they got from a sample. And then what we're trying to guess is the parameters. So we take a sample where we get statistics, and then we try to use those statistics to guess the parameter of a population. So we're using the statistics to try to guess the parameter. And it's not a perfect system. A lot of times I mean, the one we're very familiar with is polls, because we do that a lot. And people will say, well, the polls were wrong. Well, the polls weren't wrong necessarily. I mean, you can take a bad sample or have bad things, but typically what's happened is you have to understand that a sample is just a sample. And no matter how good you are at taking that sample, it's not going to exactly match the population. And so usually there's a range, and we'll talk about this when we get into things a little bit more, but usually there's a range. They'll usually say something like, I don't know, this yes, no poll. Oh, there goes my darn pen again. So this yes, no poll had the yeses at 35%. Oh man, sorry guys. I don't know why it does that sometimes. I'll check it out and it'll seem to be working just fine, and then all of a sudden it invariably happens when we're in the middle of class, of course. Try this again. So say the yeses were polling at 35% and the no's were polling at the remainder 65%, but you'll see it'll say something like plus or minus 3%. That means that this yes could actually be as low as 32 or as high as 38, and the no's could be anywhere from 62 to 68. So and of course they would balance each other out. If one went down, then the other one would go up. But this, we can never be perfect. So when you see this in a poll or something, that's important. That's telling you how much they think it could go up or down. And that could be quite a difference. I mean, 32 up to 38, that's a 6% difference. So, so anyway, we're just trying to guess. We can't be perfect because we can't sample the entire population. So there is a general rounding rule that they're going to talk about with measures of central tendency. I don't think you guys have a slide for this. I just didn't think it was worth you guys printing it out or anything. But the basic rounding rule is that rounding shouldn't be done until the final answer is calculated. So you want to use parentheses on your calculator. You're probably not going to use a spreadsheet, but you can use parentheses. The other thing you can use is on a lot of the modern calculator is you'll have an answer button. So when you're doing your calculation, rather than taking a number that you see on your screen and writing it down, say to 2 decimal places, for your next calculation, it would be better to do the calculation by pushing the answer button, which will give you the number from the last calculation. So whatever you calculated last, it will put into the calculator for this button. So let's say you calculated something and you got a number, and the next thing you want to take 55 and divide it by that number that you got in the prior question. You would say 55 divided by answer, and then that answer would be from the prior question or from the prior thing that you typed in. That's really important because otherwise you'll get your decimals messed up. If you do a bunch of, it's called intermediate rounding. If you do a bunch of rounding throughout the problem, every time you do that, you make a little bit of an error, and you just carry that error through, and it ends up with your answer being wrong. So does anybody have any questions on any of that? I know this is all just kind of build up stuff. We haven't actually even done anything yet, but does anybody have any questions in general? Okay, so we're going to look at, and please don't hesitate to ask me if you have something. So the first thing we're going to talk about is the mean. And this is the formula for the mean. And it looks really, really intimidating. But all this is saying is add up all the numbers and divide by how many there are. This is for a sample. This is for a population. But you'll notice the formulas are really just the same. Add everything up and divide. So what does all this stuff mean? What does this big E thing mean? That's all kind of important. So before we do one, I'm going to talk about that. So did I talk last week about how in statistics, yes, I'm almost positive I did. We talked about how in statistics the sample usually gets a regular letter and the population gets a Greek letter. We talked about that, right? Do you guys remember if I did or not? I guess it doesn't really matter because I'm gonna say it again, but you guys are still hearing me okay and everything, right? Everybody's very quiet this morning.
Yeah, I can still hear you.
Everybody's good? And did we talk about that last week, about the variables, the Greek letters versus the regular letters?
I think so. I'm not entirely sure though.
Not entirely sure? Okay. Well, let me just kind of say it from scratch as if we hadn't said it. So in statistics, if you are looking at a variable for a sample, very often this is given as a regular alphabet letter. So if it's a sample, they'll use a regular alphabet letter. So in this case right here, the sample mean is represented with the variable x with a bar over it. And that's literally just called x bar. That's how you read it. So the sample mean is x bar. And then if you have a variable for the population, remember we're trying to guess the variable for the population. We're trying to guess the parameter of the population. If you're talking about a population, that will almost always be a Greek letter. So in this case, you'll notice this little symbol right here. I know it kind of looks like a U, but it's actually like a little M. It's the Greek letter mu. So the population mean is mu. Again, it kind of looks like an M when they print it here, but it's actually, let me draw it again. It's actually an M, kind of a cursive M. So it's like this. It's like an M. And that's called mu. So this is x bar, and this is mu. Okay? And this is a general thing that happens all the way through the book. If it's a sample, you'll typically get a variable that's a regular alphabet, and for a population, you'll get a Greek letter. I would really, really highly recommend that you start making a set of index cards for yourself and learn these variables, because I've had students that'll say, well, I really understood the material, but when I looked at the formula sheet, I didn't know what the variables on the formula sheet were. First of all, if you really, really understand it, you probably know what the variables are, because that's kind of part of the understanding. But also, the formula sheet doesn't do you any good if you don't know what the letters in the formula are. So it's really, really important that you learn these. So for instance, I would start making a set of index cards, and from what we just did, on one side of your card, I would put sample mean, and on the other side of your card, I would put X bar. So this would be like one card front and back. And then I'd make another card that says population mean on one side, and on the other side it says mu. And use these cards, and you can shuffle through them either way. You can have the names up with the variables hidden. So you look and you say sample mean, okay, that would be an X bar, and you flip your card over. Or you could do it the other way. You could look at the symbols and then say, okay, X bar, that would be the sample mean, and flip your card over. But I can't tell you how important this is, because when you use the formula sheet, let me see if I can pull the formula sheet up here really quick. I'm not going to spend a lot of time looking for it. See if I can find it in my files really quick. Yes, here it is right here. So let me show on the formula sheet how this is going to be important when you're looking at it. This is what you can use on the test, is this formula sheet. And you can find it either in Connect Math or you can find it in D2L. It's both places. In Connect Math, it's under, I think it's under resources reference or reference resources, something like that. And then in D2L, it's got its separate module. It just says, literally says important formulas and tables. Okay, so here it's pulling up. And so this is the sheet that you can use on any of your tests. And you'll notice it doesn't have any formulas until chapter 3 because we didn't really have any formulas in chapter 1 and 2. But if you're looking at this formula sheet and you're trying to use, you know, one of these formulas and you don't know what mu is or what an x is, or what one of these little, this is a sigma and an s, if you don't know what those mean, the formulas aren't going to be of any help to you whatsoever. So you have to know what all these letters mean in order for this formula sheet to be of value to you. Does that make sense? Is everybody kind of good with that?
Yeah.
Okay. Are there any questions about that formula sheet?
So the like the E looking letter next to the X on the sample mean formula, so that just means like the sum of
Yep.
all the values, right?
Right, right. And I'm gonna talk about that right now, actually.
Okay.
So good way to segue into my next discussion here. All right, so we've got the formula that they have for this, and what they had on the formula sheet is that in order to find x bar, you take the sum of the x's and you divide it by n. So what do we mean by the sum of the x's? Well, that just means you take all the values that are in your data set and you add them up. So sum of just means add them up. So you were exactly correct. So this x bar, you calculate by taking all the x's and adding them up and dividing by n. So take the first x, the second x, the third x. That's all these things mean is x1 is just the first data value. x2 is the second data value. So if you have, you know, 10 test scores, you just take the first test score, the second test score, the third test score, add them all up. What do you guys think the n means? Based on what you know about averages, or means, I should say.
Is it like the total number, like the number of categories, like the total?
Yep, exactly. So it's the number of data values. So again, here's another card you can do. So the number of data values, and then on the other side, put n. Okay, or the number in the set, if you want to say that, number of things in the set. And so in this case, if we had 10 quizzes, we'd add up our 10 scores and then we'd divide by 10. So how does the one for the sample or for the population differ? It really doesn't. It uses the letter mu because it's talking about a population. So say you could get all the data values from the population, you would still add them all up and you would divide by how many there are. We really don't see, you probably don't need to make a card for this one because we really don't see a capital N very much. Remember, in real life, you usually can't sample the entire population. And so we will most often just see this lowercase n, which is the number of data values in the sample. Okay? So the next thing, and again, I didn't put this in your notes just because I didn't think it was worth you having to print it out. But when you're doing a mean, and actually when you're doing a lot of things in statistics, when you're done calculating it, you want to take your final answer to one more decimal place than occurs in the raw data. So say the raw data was whole numbers. So if the raw data was whole numbers, then we would want our mean would be to 1 decimal place, because we're supposed to take it one more than it is. So if the raw data was just whole numbers like 10, 15, 17, 22, when we did the mean, we would say, the average is 15.7. You take it to one place further. Now, how much do you have to worry about this? Not really much at all, because in your homework, every time in Connect Math that they want you to round it, it'll tell you where to round it to. It says round your answer to the nearest 1 decimal, round your answer to the nearest 2 decimals. And on the test, most of the questions are either multiple choice or, again, I tell you where to round it to. So don't worry too much about it, but then this way at least you kind of have in your mind, what's the rationale? Why are we doing this? So they usually take it 1 decimal past whatever the raw data was. So let's go ahead and look at this one. The example they have here is, this is a touchy subject this week. Not a touchy subject, but a relevant subject. So the number of calls that a local police department responded to for a sample of 9 months is shown. So what we're saying is this police department, in 1 month they had 475 calls, in another month they had 447 calls, and so on. And it says it's 9 months. Okay. So in order to find the average of that, you just sum up the x's. So in this case, 475 plus 447 plus 440, etc. And then you divide by 9. So the total of calls over the 9 months is 6,243. Divide that by the 9 months, and your mean number of, I don't know what they call it, incidents. I wonder if that was left over from a slide that they changed. But the mean number of calls in a given month is 693.7. And you'll notice they rounded that to 1 decimal because the data was to whole numbers. So is everybody really comfortable with how to do a typical mean?
Yeah.
Everybody's good with that? Okay, because we're going to talk about next, we're going to talk about a mean from a frequency distribution. So this really bothers people for some reason. I'm going to try to take this kind of slow because it seems to be troublesome for people a lot. The calculation is not that difficult. It's just remembering what to do. So I think it's on our formula sheet. Let me see here. Yes. So this is a mean for group data. So we're supposed to take the sum of all the frequencies times their x sub m's. Well, x sub m is a midpoint. And then we're supposed to divide it by n. So let's see, what the heck are they talking about here? We don't really want to try to just memorize formulas or just use formulas without kind of understanding what we're doing. So why would you multiply the frequencies times their midpoints? Well, what we're given here, we don't have the raw data. So we don't have all this listed out. We don't know exactly how many, I mean, I guess if we look back at chapter 2, I think we had it, but if this was all we were given, we know that there's one runner that ran somewhere between 5.5 and 10.5 miles. But we don't know exactly what they ran. We don't know if they ran 6 miles, 7 miles, 8 miles, 9 miles, or 10 miles. So this one runner ran either 6, 7, 8, 9, or 10. But do we know which of those that runner actually ran? Do we actually know which of those distances the runner recorded for that week?
No.
No, we don't have an actual number. We only know it's somewhere in that boundary of values. So what we do is we say, well, since we don't know whether it was one of these, let's kind of cut our losses as best we can and guess that it's 8. So 8 would be the midpoint of these boundaries. If I took 5.5 plus 10.5, that gets 16. Divide by 2, I get 8. Or if I list the values out like this, you can see 8's right in the middle. So the midpoint for this class is 8. Is everybody okay with that? Okay, I'm going to do something really quick. I'm going to see here if I can make this bigger. Aha, there we go. It's a little blurry, but at least we can see it a little bit better. Okay, so now if I have 2 people in this category, 2 runners that ran somewhere between 10.5 and 15.5, again, they might have ran 11, they might have ran 12, they might have ran 13, 14, or 15, but I don't know which one of those. So I'm going to say, well, again, let's just kind of cut the middle of that, take the average of it, and assume that they both ran 13. Because I don't know what they actually ran, so I'm hoping by using the average that I'll be as close as I can to the total. But it could have been 2 11s or 2 15s, or it could have been a 12 and a 15, but we don't know that. And so we're going to assume that that the 2 runners had 13 each. And then you just continue that. So this one would be an average of, we're going up by 5, so this would be 18. The midpoint of this would be 23, 28, 33, and 38. Is everybody okay with where I'm getting those midpoints from? Does anybody have any questions on that?
No, I'm good.
Everybody's good? Okay. So that you find those midpoints. And so we know, whoops, I lost my work here. Here we go. So we know that those are the midpoints, and that's what we're assuming for these runners. So I'm going to use this, and I'm going to say, well, let's write out what our raw data is now. So we're kind of basically making our own raw data set by doing this. We're going to find an easier way to do it, but let me show you the theory behind it. So we're saying there was one runner, we're going to assume they ran 8 miles. So there's 1 8. There's 2 runners we're going to assume ran 13 miles. So there's 2 13s. Then there's 3 runners that we're going to assume they ran 18. There's 5 runners we're going to assume they ran 23. So we've got 5 23s. 4 that ran 28. 3 that ran 33. And 2 that ran 38. So I basically like reconstructed my assumed raw values. Okay, it's probably not exact, but that's what I'm going to assume it was. So what would I do with this to figure out the average? If I now know here's my 20 runners, these are the amounts they ran, what would I do with that to figure out the average?
Add them together.
I'd add them all up, right? So, and then what would I divide by?
The number of classes.
Right. So I would say, no, not the number of classes, the number of, because the number of classes is 3, 4, 5, 6, 7. I want to divide it by the number of actual values. So what am I going to divide by?
The frequency total?
Yep, I'm going to divide by 20. So I'm going to add those all up, and I'm going to divide by 20. So I'm going to take 8 plus 13 plus 13 plus 18. That gets really tedious, but I'm going to do that all the way up to my last 38. And then I'm going to divide it by 20. And that would be the average of this data. Now, that's really, I mean, we don't want to have to write out this assumed raw data every time. We don't want to have to add up all 20 values or however many values there are every time. So if you were adding up, let's pick something out of here. If you were adding up 23 plus 23 plus 23 plus 23 plus 23, what's another way to add 23 or calculate 23 plus 23 plus 23 plus 23 plus 23? It's another way to do that. If I want to add up 5 23s.
You multiply it by 5, right?
Exactly. So if you go back over here to your table, I'm going to take 23 times 5 because 23 times 5 is 5 23s, which is what's in our assumed raw data. So rather than having to list them all out, I could just say, well, I want 5 23s. So what is that? 5 23s would be 115. Correct me if I'm wrong, I didn't put that on the calculator, but 5 times 20 would be 100, 5 times 3 would be 15. Yes, that's correct. Okay, so you're going to do that for all of them. So I'm assuming there's one person that ran 8 miles, and so I get 8 from that. And this is just a shorthand way of adding up those totals. 13, I'm assuming 2 runners had 13 for 26. That 3 runners had an 18 for 54. And you just calculate these all out. So 28 4 times would get us 112. 33 3 times would get us 99. And then 38 2 times would get us 76. Okay, so I write all those values down. Are you guys okay with where those all came from? Just take the midpoint that we calculated that we're assuming is what they run, and we multiply it by each of the frequencies. And that would be the same as if I added up all of these. So far, so good? Okay, well, we have to add those all up now. 8 plus 26 plus 54 plus 115 plus 112 plus 99 plus 76. Oops, I missed one of my plus signs here. Okay, so we've got, this totals up to 490. So again, what do I want to divide my 490 by?
Total frequency.
Total frequency. So 490 divided by 20 runners. So we have 490 miles total is what we're saying, and we have 20 runners. So we're gonna, that looks like rumors. So we're gonna take the 490 miles total that we think they ran and divide it by the 20 runners to get an average of 24.5. And I don't even have to put approximately because it comes out exactly. So that comes out to be 24.5. So the average of this grouped frequency distribution, or this, what they call in the table, oh, what did they call it on the sheet? Yeah, group data. Okay, so the average for this group data is 25.5 miles. Remember, this number should be somewhere in this area. This one was pretty symmetric, so our average came out really, pretty much in the middle. If this was skewed, like if it was it was much heavier in the lower numbers, and then kind of a few down here, that would skew it. So our average would be more down here. Does anybody have any questions with any of that? This one, I mean, I can tell you without a doubt, this will be on the test. I mean, there's just no, this is on the test. Make sure that you know how to do this. Okay. And the key here is you got to remember to get those midpoints, then multiply by the frequencies, and then don't forget to divide by 20, not by the 7 classes. Okay. All right. So the next thing that we're going to do, that's a grouped frequency. The next thing we're going to talk about is median. Let me get this all cleared out. And we're going to talk about median, and we're going to talk about mode. Geez, if I would have paid attention, I think I might have just changed these slides this week. Use some different data. Okay, so in order to, oh, this is, I put this up here. This is their nice little version of the midpoints with the, you know, 1 times 8 is 8, 2 times 13 is 26. So this is their nice little example of how to calculate that. What I meant to put up is, hold on a second, because that's not the slide I meant to put up. I meant to put the one for median. Here we go. Okay, so the next thing that we're going to talk about is how you find the median. And the median is the midpoint of what they call the data array. So what they mean by the data array is just the data in order. So when they say the data array, that's just a fancy way of saying the data in order. We usually do least to big, like smallest to biggest, but you could actually do biggest to smallest. It wouldn't really matter. So the data array is the data put in order, and the median would be the middle number in that. So example of this, we've got the number of police officers killed in the line of duty the last 11 years. We've got the raw data here, and if we were going to do the median, if we're going to do the average, we don't have to put these in order. We just add them all up and divide by 11. But because we want to find the median, we need to put them in order. So here's our data. We look for the smallest number. So the smallest number is 122. And then we just keep going and putting the next smallest. So the next one is 141. The next one is 149, and so on. And so we list those out until we have all of them listed. They have to be in order, because if they're not in order, you could make anything the median by how you ordered it. So they have to be smallest to biggest or biggest to smallest. Okay, so now this data value, or these data values, we have 1, 2, 3, it's 11 years. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and I want to split that in half. Well, where's the middle of 11 values at?
6th value.
Yeah, the 6th value, right? Basically, we want to put 5 values below and 5 values above. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That puts 157 solely in the middle of those numbers. So 157 is the median. Again, I think somebody was lazy when they made the slides from the last edition. They forgot to change the words on the answers. So 157 is the median. Now, this changes a little bit if we have an even number of data values. So that's what we're going to look at next. In the next one, it has the number of tornadoes that are in an 8-year period. So again, what we're saying here is in one year, there were 684 tornadoes in the United States. In another year, there were 764, and so on. So I'm going to write over here to the side, because I like to do it indicated a little different than they have it. But I'm going to put these in order. So 656, 684, 702, 764, 856, 1,132, 1,133, and 1,303. Okay, so when I do this and I have 8 values, if I go, 1 here, 2 and 2, 3 and 3, 4 and 4, the middle falls right here. So it's not like this one where I can actually pick a number out of the data set that's right in the middle. Here, my middle falls between 2 numbers. So what do I do with that? It's actually fairly logical idea. What are we going to do if we fall in between 2 numbers? What are we going to use for the median?
The average of those 2 data points.
Exactly. I'm going to take those 2 data values. I'm going to say what's right in between them. What's the average of them? I'm going to take 764 plus 856 and divide it by 2. And that comes out to be 810. So the median is 810 in this case. 810 is not actually one of the values, but it's the average between the 2 middle values. And so that sometimes you'll do, find a number that's right there in the data set. Sometimes you have to do that little calculation. But both times you're looking for the middle of the number set, of the data set. Does anybody have any questions on that one? Okay, I'm going to do something really quick because I think it'll help us later. Later we're going to talk about what are called quartiles. And quartiles is basically finding the medians of each half of the data set. So in this case, if I was going to try to find what we call the first quartile, I would look at these 5 numbers and I would say what's in the middle. And that's called Q1. And we'll come back and do some more of these here in a bit. And then up here, this would be what's called Q3 because it's the middle of the upper half. So where's Q2 at? Why is there no Q2? Why does it go Q1 and then Q3? And the answer to that is because the median is the Q2. But we don't call it Q2, we call it median. It has a special name. So something you can really liken this to is if you think about a sports game like football or basketball, a game that has 4 quarters in it. And you think about at the end of the first quarter, we say it's the end of the first quarter. But when it's the end of the second quarter, we don't call it the end of the second quarter usually, even though it is. We usually say it's halftime. So the median is kind of like halftime. It has a special name, but it is the end of the second quarter. And then after the third quarter, we say end of the third quarter, and then this would be the end of the game. So what's the purpose of this? Well, what we're saying is a quarter of the data roughly falls from 149 or below. Half of the data falls from 157 and below. And then 3/4, Q3, falls from 177 or below. And you could look at it in reverse too. Like you could say a quarter of the data is above 177, or a quarter or 3/4 of the data is above 149. And then same thing here. In this case, once I split it, I still have 4 on each end, so I would have to do the averages again. This would be the Q1. I'm not going to calculate those right now, but that would be the Q1, and the Q3 would be whatever the averages of those numbers were. So we'll come back and revisit quartiles in a bit, but that's the general idea of them. All right, I'm going to get rid of all this. Anybody have any questions on this? Okay, so that's how we do the quartiles, or the median and the quartiles. So the next thing that we're going to talk about is the mode. And the mode is really easy. It's not really very useful a lot of times, but it is very easy to compute. The mode is simply the value that occurs the most often. Sometimes we call it the most typical case. The problem with the mode is sometimes there can be no mode. Oftentimes there's one mode. But there can also be 2 modes. We call that bimodal, or there could be many modes, which we call multimodal. They do sometimes use the word trimodal, but usually once it gets past 2, they just call it multi. So in this case right here, when we've got NFL signing bonuses for some year of 8 players, 8 random players they've picked, I assume. And these are their bonuses. So they put them in order. You don't really have to put them in order. It just kind of helps you see things a little bit better. So they've put these in order, and you're looking for what occurs most often. Well, in this case, everything occurs once except for the 10. So 10 occurs most, and so the mode is $10 million. Does anybody have any questions on that one? I'm going to do an example. I don't think there's one in your notes on bimodal. Oh, yes, there is. Okay. I was going to do one if they didn't. Whoops. It's the same one I just did. Okay, so here's one where there's where it's not just a single mode. So here we have licensed nuclear reactors in the United States. So we've got 1 year, or in 5 different years, there were 104 licensed nuclear reactors. 1 year there was 107. They've got them marked out colors by us. 5 years there was 109. 1 year there was a 110. A couple years there was a 111, and another year there was 112. Well, since 104 and then the 109s, you can see we're putting them in order, kind of helps. They didn't put them in order here, but they both occurred the most. They both occurred 5 times. And so the modes, there's more than one mode here, are 104 and 109. You have to list both of them. If you just said the mode is 104 or the mode is 109, you're missing half your answer. And then if you had a data set that was, say, I don't know, let's say there's a set of test scores in a class, and there was 10 people in the class. So you had 73, 77, 79, 81, 83, 84, 91, 95, 99. We'll let the last person have 100. Okay, so if these were your test scores in a class, what would be your mode? Of these test scores?
There isn't one.
There isn't one, exactly. So when you're talking about a set of values where nothing occurs more than the others, you would say there's no mode. Be really cautious. Don't say the mode is 0. Saying the mode is 0 means 0 occurs most often. Here there is literally no mode. Okay, so there's no mode for the static because everything occurs the same number of times. Even if they all occurred twice, if every single one of them occurred twice, there would still be no mode because nothing occurred more than the others. Okay, so the next thing that we're going to talk about is a modal class. I should have talked about this when we were talking about the group frequency distribution. I didn't think to do it. So this is the same data we used for the group frequency mean. And hold on a second, I chopped part of it off. And what they're asking for here is what's the modal class? Well, your homework might ask what the mode is, but I usually, if I'm going to ask it on a test, I usually put it with that other question. Remember I said you're going to have to find the mean of one of these tables? I usually put with that same question, I ask what the modal class is. And the modal class is just the class that occurs the most often. So in this case, 20.5 to 25.5 occurred 5 times, so that's the modal class. If by chance your homework asks you what the mode is, then you use the midpoint for that class, which the midpoint was 23. So you'd say the mode is 23, the modal class is 20.5 to 25.5. Like I said, I wouldn't ask it like this on the test, but the homework might. Okay. So we just have a couple things left for section 3.1. We need to talk about the weighted mean, and we need to talk about hold on a second, lost my train of thought here. We want to talk about the weighted mean, and we also want to talk about the mid-range. So mid-range is very often confused with median, but the mid-range is actually the middle of the range of values. So here's the example that they have. I don't like this example very well. I'm going to use one of our other examples and give you the mid-range for that too. But the mid-range is literally, it just means if you were to graph these out, in this case, the lowest value is a 3 and the highest value is a 157. And so the mid-range would be right in between those. So it's the average of those two. So it's 157 plus 3 divided by 2. So in this case, that's 80. So let me show you how that's not the same as the median. Let me go back to one of our prior slides. Take our one that we did for the median. We'll do the tornado one here. So remember here with the tornado problem, we said that the median was 810 because it fell in between the 764 and the 856. And so the median was 810. But that's not what the mid-range is. The mid-range, you would think of, okay, the lowest value in this data set is 656. The highest value in this data set is 1303. And so this is the highest value, this is the lowest value. And so the mid-range is literally just what's right in between, or what's the average of the very highest and the very lowest. So 656 plus 1303, and we divide that by 2, you would get 979.5 for a mid-range. So the mid-range is 979.5, where the median was 810. Any questions on that one? We don't do mid-range a lot, but they do ask you a couple of them on your homework. Just don't get it mixed up with median. Okay, so when you're thinking mid-range, you're looking at the range of values from 656 to 1303, and what's the middle of those? Not the numbers lined out from smallest to biggest, what's the middle number, but what's the middle of the whole range of values. Okay, so the next thing that we're going to talk about is I think I skipped a slide. So let me do that slide that I accidentally skipped here. One thing that's kind of weird about the mode is the mode can actually be a category. So the mode doesn't have to be a number. So in this case, this is the number of registrations for 6 counties, for the boats in 6 counties in Pennsylvania. And in this case, the one that occurred most often was Westmoreland. And so the mode of this data is actually Westmoreland, which seems kind of strange for the mode not to be a number. The mode's the only thing that can be something besides a number. But in this case, you wouldn't say the mode is 11,008. That's how often it occurs. We want to say what occurs most often. So what occurs most often are the registrations in Westmoreland. So again, you may run across that in your homework. I wouldn't probably ever ask that in a test. Not probably, I won't ask that in a test. All right, so like I said, we have A weighted mean is the next thing that we need to talk about. And I'm going to write off here to the side. Again, this is one, it's definitely going to be on the test. Pen again. Now, how are you going to see it on the test? On the test, it's going to be a problem where you have to compute a GPA. A GPA, computing your GPA is computing a weighted mean. And so you'll have some other ones in your homework, but on the test, I'm going to give you one about your grade point average. So what the formula says in general is that you take the weight times the score plus the weight times the score and so on. So if this was a grade, let's use our homework because they don't give an example of this. So just so you know how to do it on your homework. So let's say in the class you did on your homework, you got on your homework, you did 95, you got a 95 on your homework. On the midterm, you got an 81, and then on the final, you got an 88. Now ours is fairly even between the three things, but it's not exactly even. So the homework is actually worth 30% of your grade, midterm is worth 35%, and finals worth 35%. So what the computer does to calculate your grade now, it knows that on the homework you got a 95%, on the midterm you got an 81, and final you got 88. It would take 0.3 times 95, then it would add 0.35 times 81, and then it would add 0.35 times 88. And that would give you your overall grade. And it'd be just a little bit different than if we added these all up and divided by 3, because the homework doesn't weigh quite as much as the midterm and the final do. So that's what they mean by weight. So the weight is the percentage like this, and then the X1 would be the actual value. So it's weighted at 30%, you got a 95. It's weighted at 35%, you got an 81. So is everybody okay with what that general formula means? Any questions on that? You're going to add those up. So the sum symbol, add up all the weights times their x's, and then you're going to divide it by the weights. Well, in this case, we didn't have to divide it because the weight is just, it totals up to 1. I mean, it totals up to 100%, which is 1. So dividing it doesn't really matter. Okay, so how do you do that on a GPA? This is what's going to definitely be on the test. So when you're talking about calculating a GPA, you have, let me zoom in on this a little bit. So you have your grades. And in this case, this person took English Comp, got an A, took Intro to Psych and got a C, took Biology and got a B, and so on. Well, why can't we just take their grades and add it up and average them? And the answer is because the classes aren't all worth the same. You'll notice here that it says English Comp is a 3 credit hour class. And then Intro to Psych is also a 3 credit hour class. Okay, so those are both 3 credit hour classes. But Biology is a 4 credit hour class, which is pretty common because usually your science classes have a lab that goes with them, so they're usually like a 4 or 5 credit hour. And then PE, in this case, is 2. I think at Lone Star, all the PE classes are worth 1 credit hour. But anyway, this one's worth 2. So we have to take that into account, that this B is weighted more heavily because that's a 4 credit hour class, and that this C is weighted more heavily, or more heavily than the PE anyway, but not as heavy as the Biology because it's 3 credit hours. That matters. If we don't take that into account, we're not going to get the right average. And so in order to calculate the average, we first have to convert the grades to points. And this is a little bit confusing. If you've just graduated high school, this is probably like a new thing to you because you're like, wait a minute, the different, how many credit hours the class has matters. It does. And it's weird because in high school, most of your classes are either, most of them are the whole year. Sometimes you'll have a 1 semester class. And so that's considered like a half of a credit, depending on how your high school does it. They might consider each semester a credit, or they might consider a year a credit, and then a semester would be like a half a credit. So, but in college, your classes can vary anywhere from like 1 credit hour up to like 5 credit hours. And so they have to take that into account when they're computing your grade. So we typically, for our grading system, an A is a 4. That's why we say when somebody has, like an A average, we say they have a 4.0. I know sometimes it can go above 4 points now, but in the original system that was the highest. A B is a 3, a C is a 2, and a D is a 1. And then, of course, if you get an F, you get no credit. And so if somebody said they took a 3 credit hour class and they got an A in it, what that basically means is that you get 4 points for every credit hour in that class. You get 12 points for that class. Could you have gotten any more points in that class? What's the most number of points you could have gotten in English Comp if it's a 3 credit hour class?
12.
12, exactly. That's the highest, right? That's it. But look here, in Intro to Psych, it's a 3 credit hour class, but you only got a C. So you only earned 6 points in that class. Sometimes these are called PowerPoints. Not like a PowerPoint like we're doing right now, but they're called like PowerPoints, like your total points. And so 3 times 2 is 6 points or 6 PowerPoints. How many could you have earned in Intro to Psych?
12.
You could have earned 12, right? So you only earned 6 of the 12 possible. And then in biology, it's a 4 credit hour class. You got a B, which is a 3. So you earned 12. You could have earned 16 because if you got an A in that class, you would have had 16 points. So there were 16 points possible. You earned 12 of them. Or this person, I shouldn't say, it's you. And so on. So you do that all the way down. Now, in the PE class, you could have earned 8 points and you only earned 2, or this person only earned 2. So if we total that up, that's 32 PowerPoints that you've earned. That's where this top number comes from. So the sum of the weight, so in this case, 3 times 4 plus 3 times 2 plus 4 times 3. So that's what we did over here. And then you add up on the bottom the number of credits, not the number of classes. You don't want to divide by 4 classes. You also don't want to add up these. These don't have any meaning when you add those up like that. What we're adding up is how many credits did you attempt that semester. So you attempted 12 credit hours, or this person did. And so 32 points earned out of 12 credit hours is an average of 2.7. So that would be like a high C. Or actually it'd be a low B. It's actually considered a B minus. So like a 2.33 would be considered a C plus, and a 2.66 would be, or 67 would be considered a B minus. So this is like a B minus. Okay, so that's how you do GPA. And like I said, there will definitely be one of these on the test. Absolutely, positively be one like this. Okay. For one thing, I just think it's good for you to know how they calculate your GPA, where it comes from, and all that. So I think once you get done with a intro to stats class in college, that you should really know how to calculate your GPA, just kind of for the point of it and also for the usefulness of it. Okay, so the next thing that we're going to talk about really quickly, I'm going to zip through these really quickly, is the properties, like what are the good things and the bad things about each of the things that we talked about, each of the measurements that we talked about. So we've got the properties of the mean, We have the properties of the median, and we have the properties of the mode. Okay. Oops, I got ahead of myself here. I'll move that over. Do the next one. Okay, so here's our three things. We have mean, median, mode, and properties. Well, the properties of the mean, what's nice about it is that we use all the values of the data. So it takes into account all the values of the data, and that makes it vary less than the median or the mode can. The median and the mode can vary quite a bit if just one data value is different. We use the mean for a lot of other statistics, such as computing the variance that we're going to do in a bit. It's usually unique. Usually when we calculate the mean, it doesn't actually come out to be one of the data values. And a lot of times it doesn't even come out to be one of the possible data values. So like 2.7 we got for that GPA, you can't have a class where you get a 2.7 because the only choices are 4, 3, 2, 1 for A, B, C, D. And so that's what we mean by unique. Like it's not usually even a value that you could get. You can't use it though when you have open-ended classes. Like if you just say this much or more, you can't use mean. You have to actually know where it stops and ends. And it can be affected by high or low values, which are called outliers. The median gives a type of a midpoint. It's really used when we want to know, like, are you in the upper half or the lower half of the group of values. It can be used for open-ended because if you said there's 5 values that are this much or more, it's still 5 values. So you still know how many to count for the top half and the bottom half. And because of that, it's kind of affected less by the mean, because even if you have a really high value, the median could still be in the middle, okay? Or the median could still be in the same location. So say you had, I don't know, 2, 5, 7, 10, 11, 50. The median is right there. This 50 would pull the average way up, but that 50 doesn't affect the median any more than, say, a 12 would. If I had a 12 there, I'd still have the same median, but that would affect the mean a lot. So the median is not affected by those extremely high or low values as much as the mean could be. Again, if I change that to a 50, that would change the average of these 6 values tremendously, but it wouldn't change the median at all. And then the mode, it is easiest, and you can use it with nominal data like the Westmoreland boat registrations. But the problem is it's not always unique, or it may not even exist. The mode is actually it's not used a lot because it's not that useful. And then the last one is the mid-range. And again, kind of like mode, it's easy to compute and it gives you a type of midpoint, but it can be really affected by high or low values, just like the mean is. Again, if I use 2, 5, 7, 10, 11, 12, the mid-range would be whatever the average of 12 and 2 is, so it'd be 7. But if I threw the 50 in there, then the mid-range would be 26. So just changing one value changes the mid-range from 7 to 26. So it's really affected by extremely high or low values, just like the mean can be. So anyway, just some benefits and differences between them. And then the last thing here, for 3.1, I don't know why this is not copying, just a second. Okay. Is just we're going to revisit the skew idea. So if you have a set of data that is in a bell shape, basically if it's symmetric, then your mean, median, and mode are all going to be right in the middle. This is the average, it's what occurs the most, and it's also the middle. Whereas if you have a set that's skewed, remember this would be considered skewed right because it tails off to the right, that pulls your mean up above your median, and it actually pulls the mode down. So if it's skewed right, the mean will be higher than the median. If it's skewed left, or skewed, negatively skewed, that pulls the mean down below the median. These numbers that tail off pull the average downward away from where the middle is. So just a real, we kind of talked about that on Thursday, but just a revisit of that. Okay, so now this next one, I don't think it's labeled. If it isn't labeled, it should be. But this is the start of section 3.2. I don't think it's labeled. So now in section 3.2, we're going to start talking about measures of variation. In other words, how much does the data vary among the different data values? And the first thing that they're going to talk about is the range. So if you're computing, a lot of times people will say the range of values. So if we think about the one that we just did a bit ago, I think the range of values went from, this was when we were doing the mid-range. Let me go back to the mid-range. So here, we said that the mid-range was 80. But the actual range, in this case, 3 is the lowest, 157 is the highest. We said the mid-range was 80. But the actual range is just equal to 157 minus 3, or 154. It's how far apart these two values are. So those two values are 154 apart from each other, so that's the range. So they're spread out across 154 values from lowest to highest. That's the range. Okay, it's very easy to compute, but it doesn't tell you a whole lot about the data as far as how spread out it is, because it's just that, you know, that one number, and it just talks about how far the lowest and the highest are. More valuable to us is going to be the variance and standard deviation that we're going to do in a little bit. But let's talk about range for just a moment more. So we're going to look at these examples of these paint cans. And it asks us, it says we got these two paint brands. They're trying to test them. And brand A, these are the number of months that these 6 cans of paint lasted before they faded. So, you know, the first can lasted 10 months before it faded. The next can lasted 60 months before it faded, and so on. Then they have brand B here, and they do the same thing. So what does this data tell us about the two brands? So this one, if you compute the range, you get the highest value is 60, the lowest value is 10, so you get a value of 50. If you do this one, the highest value is 45 and the lowest value is 25, so you get a range of only 20. So the range on this is 20 and the range on this one is 50. So what does that tell us about the paint? Well, let's also do the means. If you were to calculate, and we'll just kind of cheat a little bit here, I know the answer to this already. If you were to calculate the average for this, we're thinking of this as a population. This is supposed to be like a new brand of paint, so there's only these 6 cans in existence. So we think of this as a population, The average is 35. But this one also has an average of 35. So if somebody just told you the average of brand A is the same as the average of brand B, you might say, oh, the two paint brands are virtually the same. But what is this one having a range of 50 and this one have a range of 20? What does that tell you about the actual results of the test? Anybody have a guess at that?
Brand B is more consistent with its data values.
There you go. You are exactly right. So by saying this only has a range of 20, this means it's more consistent than this brand is. This brand is more variable. So these months for these 6 different paint cans are more spread out than these months are. And so if you were going to make an advertisement for these, you could say things like, brand B is more reliable. Brand B is the one you can count on. You could say it's more consistent. So those would be things that people would like about it. You know, this one is kind of a, kind of a gamble. You may get lucky and get a can of brand A that lasts 60 months, but you could also be unlucky and be that person that gets a one that lasts 10 months. And shoot, what if you're painting your house and you use half, this can on half of the house, or not half of the house, but, half of the front of your house, and you use this one on half of the other half of the front of your house? Well, this one's going to start to fade while this one's still okay, and your house is going to look all wacky. So consistency in products is important. And so in this case, when you're talking about averages being the same, you're going to go for, okay, well, if the averages are the same, I'd rather probably get that one that's more consistent, more reliable. Okay, so that's range. And the next thing that we're going to talk about is variance and standard deviation. And variance and standard deviation, we're going to do, I'm going to make this really clear. We're going to do it first the hard way. But then we're going to learn an easier way, okay? So we're going to do, just for the theory of it, we're going to do the hard way, just to understand where it comes from. And then we're going to use, but what I want you to use when you're doing your homework and stuff, use what's called the shortcut method. Okay, there's on the formula sheet, there's there's 2 formulas for variance and standard deviation. One is the theoretical formula, and the other one is literally on the sheet. It says shortcut method. That's the one you want to use. Use the shortcut method, okay? We're going to start with the harder way just so we kind of understand what variance and standard deviation are. So, population variance is the average of the squares of the distance each value is from the mean. I'll show you what that means with the little picture here in a minute. The standard deviation is just the square root of the variance. So let's do this in variables. Remember, everything that's a population is usually a Greek letter. So population variance is usually represented with this symbol. That's a sigma. It's a Greek letter S called sigma. And we usually call the population variance sigma squared because the standard deviation is just sigma. It's the square root of that. So if you take the square root of something squared, you get the thing that you started with. So here, if I take sigma and square it, if I take the square root of it, I get just a sigma. What do you guys think? You okay with the terminology on that? Again, make yourself a card. On one side of the card, put sigma squared. On the other side of the card, put population variance. Make yourself a set of cards with these on them and study them, because it will help you tremendously when you're taking your test, if you know really well what these are. So this would be population standard deviation. Okay. So what are these? Well, they're measures of variance. They're a better measure of variance than range is. So if the sigma is high, that means that the data is spread out. If the sigma is low, it means the data is less spread out. So it's a measure of how spread out the data is. And we'll do an example of this here after we talk about the formula and the uses. So the variance and standard deviation are used to determine the spread of the data. They determine how consistent it is. And then we also use it to determine the number of values that fall within a specific interval. That's called Chebyshev's theorem. We'll talk about that in a bit. And then it's used in inferential statistics. Remember, inferential statistics is when we're trying to predict. So that's statistics where we're trying to make predictions or do a comparison between like a cause and effect, like does the input affect the output, that type of thing. So it's used in those inferential statistics. And here's the formula for it. But this one's the hard formula, remember. We'll have an easier one. Whoops, that's not what I meant to do. Okay, so in order to compute the population variance, this doesn't look very hard, but what we have to do is we have to compute the average. And remember, this is the theoretical. We're going to have the shortcut method is coming. Okay. So coming up, we'll have a shortcut method. But this theoretical model, you find the average, and you take every data value in the set and you subtract the average, square it, and add those all up. And then you divide by how many there are. That can get very tedious very fast because you have to do all those subtractions and you have to square them all and you have to add them all. So that's like 3 things you have to do to every single data value. And that's after you find the average. So this can get really long. Notice also though that the population standard deviation is just the square root. See, notice these are the same formula, but this one just has a square root over it. So the standard deviation is just the square root of the variance. So we're going to look at the data that we just did with the paint, and we're going to compute the standard deviation of brand A. Okay, so this was their nice slide with the average and the range on it. So we're going to take brand A here, and we're going to compute the standard deviation, the variance and then the standard deviation. So remember that the variance is the sigma squared is the sum of all the x minus mu's squared divided by n. Okay, so really quick question because it's the easiest part. What's the n? For brand A, what would the n be?
It's 6.
It'd be 6. Yep. Okay, so let's fill in some other things. We know this is 6. What do we know that the mean is? We already computed the mean. So what is the mean? It's this mu value for brand A.
Wasn't it like 35 or something?
You're correct. It was 35. Okay, so we're going to take every single value in the set. We're going to subtract 35. Then we're going to square it. Then we're going to add or divide by 6. So we have to do that for each of these. So I'm going to do it for the 10. So 10 minus 35 is negative 25, right? Then we're supposed to square that. So 25 squared, or negative 25 squared, is that 625 or negative 625? Is that positive or negative?
It's positive.
You're right. Anytime you square something, it's positive, right? Well, unless you're talking about imaginary numbers, but we're not. Okay, we're doing statistics, only real numbers here. Okay, so negative 25 squared is negative 25 times negative 25, which would be a positive number. If you're trying to type this into your calculator, two ideas here. Either just don't put the negative in front of it because you know negatives squared are positive anyway, so 25 and negative 25 squared are going to do the same thing. So you can just type in 25 squared if you wanted to. Or if you are going to type this in, you have to put the parentheses around it, because otherwise your calculator thinks you want negative 25 squared. So you have to tell it, I want negative 25 squared. So you've got to put the negative inside with the 25 before you square it, or it'll give you a negative answer. Just FYI, people get that wrong all the time. Okay, so what are we saying here? We're saying 10 minus 35 get negative 25. We're saying that this paint can was 25 months under average. And then we square that, get 625. Do that for the next paint can. So the next paint can was 60, while the average was 35. How far apart is that? Well, that's still 25 apart. It just happens to be 25 months better than the average. So it still gives us a 625 to use in our computation. So it's as far off of the average as the paint can that was 10. That's why we got 625s for them. This one was 25 low, this one was 25 high. Okay, keep doing that. The next can was 50. That gives us a 15 above average, and that doesn't give us as big a number to add into our variable, or into our variance, because it's not as far off of average. So it only gives us a 225 to use in our computation. And just keep doing that. 30 minus 35 would be negative 5 squared, which is a 25. 40 minus 35 squared is 5. And then 20 minus 35 squared is negative 15, which would be the same as the 15. So that'd give us a 225. Let me draw a little picture of this up here. Let's see if I can find some space here. So what we're saying is our average is 35. And what we're trying to figure out is all these different cans, where do they fall? Well, if you had a 10, that would fall way down here. If you had a 60, that'd fall way up here. If you had a 50, it'd be above, but not as bad. If you had a 30, it'd be below, but not as bad as the 10 was. And so what we're doing is we're saying, if this is average, how far off of average are each of these scores? That's what or each of these paint cans. That's what we're kind of trying to figure out. If we did this with brand B, these distances wouldn't be as far. So we would get a lower standard deviation for brand B because these aren't as far off of average as some of these are. And so we're trying to figure out how far off of average are we? How much does that add up to be as far as an overall distance from average? So these really vary from average as much as 25 months away. Okay, so that's kind of the theory behind it. Remember, we're going to have a simpler way to do this in a minute, but that's the theory behind it. So if we sum all these up, then we can figure out the variance. So take 625 plus 625 plus 225 plus 25 plus 25 plus 225. And that totals up to be 1750. And again, this is our sigma squared. So our sigma squared is whatever 1750 divided by 6 is. It comes out to be 291.66666 repeating. So I'm going to round that, just like the mean, I'm going to round it 1 decimal past these were whole numbers, so I'm just going to take it to the tenths. So 291.7, that's an approximation. Does anybody have any questions on that? We're not quite done, but does anybody have any questions on that one? So you have to compute the average. You have to subtract every single value from the average, or subtract the average from every single value, I should say. Then you're going to square them all and add them up. That's where I got that 1750 from. Everybody good with that? Okay. So how would I get this value? If I know that sigma is 291.7, or sigma squared, how am I going to get sigma? This is the variance.
Just take the square root.
Yep. So the variance to the standard deviation is just a square root. And the same the other way. If for chance you had the standard deviation and you needed the variance, you would just square it. But typically, like this formula, you get the variance first and then you go to the standard deviation. So do I want to put 291.7 in my calculator? What do I want to put in my calculator? Remember back a little bit, we talked about this. What I want to do is I want to put the square root of the answer that's on my calculator. So look for on your calculator, you should have an answer button if it's not an ancient calculator. On the TIs, it's very often above like the negative sign. On the graphing calculators, yeah, on the graphing TIs, it's right above the negative sign at the bottom right. So you have to push shift answer. So you push square root, and then you push second, and then the button that has answer above it. If you have any questions on that, if you're having problems, don't hesitate to Google something. So just Google it and say, you know, if you have a TI-34, just Google using ANS on TI-34, and I'm sure you'll find 5 YouTube videos on it, because they're all going to be just a little different. But if you can find that answer button, that's going to make your answer more exact. And you should get 17.07825.128, which is 17.1. And yes, if I put 291.7 in, I think this time you get, yeah, it still rounds to 17.1, but sometimes it doesn't. Sometimes making the rounding error from here to here, then this ends up being a decimal off. So this is much safer to answer from your prior question. Anybody have any questions on that before we learn the easier way to do it? Okay, so that's how you find the average for a population, or the variance and standard deviation for a population, using the theoretical method. So I'm going to put this up here really quick, but if you happen to be doing this by the hard way and it was a sample, you would actually have to divide by n-1 instead of n, because you have to kind of adjust for the fact that it's a sample. But again, we're not going to be doing this. If you've got a sample, you can use the shortcut method. Okay, so there's no need to really do it this way. And so what's the shortcut method. Let me get rid of this. Okay. So they call it on the slide, they call it the sample computational method, but on the formula sheet, they call it the shortcut method. Let me show you the sheet. So it's right here. Right here, shortcut formula. That's the one you want to use, okay? So when you're doing this on your test, you want to just use this shortcut method, okay? What did it just do? Okay, go away. There we go. And then, of course, the standard deviation, you just do this. Another thing to note, since we're talking about sample, you notice the variable is changed. So again, it's another card to add to your pile. If it is a sample variance, that's S squared. Sample standard deviation, that's an S. Why? Because we're talking about the sample. So the sample doesn't get the fancy Greek letter. The sample just gets the regular alphabet letter. The way I kind of remember it is the population thinks it's all that just because it's bigger. So the population gets the fancy Greek letters, whereas the samples just get the regular alphabet letters. So they get the samples, just this little sample. So he just gets the regular old letters, but that population thinks it's all important and big, so he takes those fancy Greek letters. So since this is a sample, it just uses the letter S instead of a sigma. Okay, so let's try this on one. The problem is they never gave us and I don't know why, but they don't give us an actual example of this. So I'm just going to make some data up really quick. So just say we had some test scores that were 2, 5, say it's a 15-point quiz. So 2, 5, 10, 11, 12, 12, 14, 15. So say that's some quiz scores in a class. One person had a 2, another person had a 5, and so on. So how would you find the S squared and then the S for that? So let's look at this formula. It looks harder. This formula looks like it would be harder, but it's actually easier. For one thing, we don't have to compute the average first. So it says take n times the sum of the x squares and then subtract the sum of the x's squared. So let's start with the easy part. What's n for this?
Not the total number.
Yep, you're right. So n would be 8 because there's 1, 2, 3, 4, 5, 6, 7, 8. So put that in your formula. So we have an 8. And then how are we going to get the sum of the x squares? What the heck does that mean? What would the x squares be? Let's start with the easier. What are the x's? What's x sub 1?
Is that just
The test scores?
Yeah, just the scores. Yeah, so x sub 1 would be the 2. X sub 2 would be the 5. X sub 3 would be the 10. Yeah, so they want us to sum up the x's squared. So these are the x's. The x squares, and I'm going to write n equals 8 up here because I kind of want to keep that, but I kind of had it in the way here too. So the x squares would just be 4, 25, 100, 121. It's just these numbers squared. 144, 144. I don't know what 14 squared is. We're past our times tables that you have to learn as a kid. 14 squared is 196. And then 15 squared is 225. Okay, so those are the x squares. And they want us in the formula, they want us to sum up the x squares. So what are we going to do with these?
Add them all together.
Add them all up. And here's a word to the wise. You do not have to write all those down. You are perfectly fine when you're doing your homework or the test or whatever to just type into your calculator 2 squared plus 5 squared plus 10 squared plus 11 squared and so on. You don't need those numbers for anything else. So you don't really have to write down 4, 25, 100 and all that. You can just type in your calculator 2 squared plus 5 squared plus 10 squared. But since we have them already, I'll go ahead and do that. 4 plus 25 plus 100 plus 121 plus 144 plus 144. I have no idea what the answer to this is because I just made that data up. I've got 959. If anybody's got something different, please let me know. I got 959. Okay, so we just figured out that, I don't want to put an equal sign there because we don't have it. I'll just say the sum of those is 959. What is the next thing here that they want us to do? It says in the formula they want to sum the x's and then square. So what am I going to do for this part of the formula? Right there. We need the sum of the x's. So what am I going to do?
Just add the test scores up.
Yep. So 2 plus 5, again, which, you know, this formula looks harder, but these calculations are so much quicker than having to go through and do all those subtractions. So you just do, you know, for the bottom one, you just do 2 squared plus 5 squared plus 10 squared plus 11 squared. For this one, you just do 2 plus 5 plus 10 plus 11 plus 12 plus 12 plus 14 plus 15. And you just do it on your calculator. No need to write down anything intermediate. So that gets you an 81. So we're going to pop that in right there. These are not the same thing. This one you square them and then add them. Here you add them and then you square the final number. So 959 is not the same thing as 81 squared. Those won't get you the same numbers. Kind of looks at first like it's the same thing, but it's not. Okay, what's our n? Down here on the bottom we need n times n minus 1. So what's our n?
Eight.
Mm-hmm. And then our n minus 1, I'm going to write 8 minus 1, but when you're doing this, it's probably easier to just write down 8 times 7. So calculate that out. What I usually do is I usually calculate the bottom and write that down. So this is like 56, because again, it's 8 times 7. And then I do the top divided by whatever I had on the bottom. So 8 times 959 minus 81 squared, I get 1111. That's unusual. And then if I divide that by 56, I get 19.8. And that's my sample variance. So how would I get my S out of that? Which would be the sample standard deviation. How would I get that now that I have the variance?
Square that number.
Not square it, but square root it.
square rooted, yeah.
Yeah. So do square root, and again, leave that number in there. Do square root of answer, and you should get about it's like 4.45, which would round to 4.5. Now, let me tell you something about Connect Math that I don't like, but I can't change it. In fact, I've told them about it, and they haven't changed it, and it kind of frustrates me because they're usually a little bit more responsive. On your homework, there are a couple occasions where this is the right way to do it. The way we just did it by taking, you know, square root of the answer and getting the 4.5, that's the correct way to do it. But there's a couple on your homework where they use the rounded value. So if you know you're doing it right and you're getting, and this is coming out like a decimal off, try using the rounded value. It's supposed to be, you're supposed to use, like I said, the whole number, not round until the very end. But there's a couple on your homework that I know they do it the other way because we've run across it in the past. So, and I still have students that'll ask about it. So I know they haven't fixed it. Does anybody have any questions on this? This is the hardest thing out of chapter 3, is doing this variance and standard deviation. Again, I'm not trying to be very, very what's the key word of the decade? I'm trying to be transparent. So being very transparent here. This will be on the exam. So this will absolutely be on the exam. So make sure that you know how to do this. There'll be one problem with a fairly small set of data values because otherwise it gets too cumbersome, where you have to figure out the variance and the standard deviation and pick the correct answer. What's that?
Will the theoretical method be on the exam?
Nope. That's what I'm saying. Like that theoretical method, we just kind of learned to understand where it was coming from, but there's no need to use it anymore because the shortcut method is quicker, easier, and gets the same answer. So, but the other way is where this all came from. And then at some point after that, somebody realized or recognized that this gets the same answer and it's easier. So now if you were doing it by hand, this is how you should do it. Okay, so let's go to the next thing we're going to talk about is CVAR. And CVAR stands for the coefficient of variation. So how could you, what would you liken this to? Why would you use the coefficient of variation? It is the standard deviation divided by the percentage, and it's used to compare standard deviations when the units are different. So if you were, this isn't exactly the same thing, but just to sort of kind of get in your head why we're doing this. Say you were trying to compare two cities, or say you have two different cities, and you were trying to say what percentage in town A, or not percentage, you were trying to compare town A graduation or number with people with a college degree. So you're trying to compare town A college grads with town B college grads. So you're trying to say, how do these two towns compare to each other in the number of college grads? Well, if you just say town A has, I'll keep the numbers simple, say they have 1,000 and town B has 500, does that really tell us that much about how these two towns compare? What else, what info are we missing here? Let's change this from town A to and town B to say this is Houston. And this is, I don't know, Waco. I know that's an exaggeration, but what do I need to know besides that Houston has 1,000 college grads and Waco has 500 college grads? Does this mean Houston has typically more college grads?
The population.
Yeah, you have to even it out, right? So you have to know 1,000 out of a total, right? You have to know what the population is in order to be able to compare. So to be able to compare Houston to Waco, we have to compare the college grads to the total population. We have to compare apples to apples. We can't say this town is better just because it has more grads. It depends on how big the towns are. Well, that's kind of what CVAR does. So with CVAR, let's say for a company, you're trying to compare the variance of their sick days to the variance of their salaries. Well, sick days would be a much smaller number than salaries. And not only that, they're different units. Sick days would be in days. Salaries would be in dollars. So when you're trying to compare two things and see which one is more variable between two data sets that are quite different, I'm not even going to say the units are different, just when you have data sets that are very different. So if you have two data sets that are very different from each other, whether it be the units or even just one's small numbers and one's big numbers, take the company again. Say you're trying to compare how much they spend, you know, the people at the company on average spend on lunch and what their salaries are. Well, how can you tell which one's more variable when one you're talking about a few dollars a day and the other one you're talking about thousands of dollars in a year? Well, those are so far apart, it'd be hard to tell which one was more variable without using CVAR, okay? Now, a really quick note, this is not on your formula sheet, but if you need it on the test, I'll give it to you. So if you have a problem on the test where you need the CVAR, I will give it to you. It'll be like right with the problem. It'll say, remembering that CVAR is S over X bar times 100%, compute the CVARs and, you know, say which one is more variable. Okay, so the CVAR is really easy. All you do is you take the standard deviation and you divide it by the average. So if I'm going to ask you to compute a CVAR, I'm going to give you S and I'm going to give you the average, and all you have to do is divide them and multiply by 100. So this is what it looks like. So we've got, in this case, the mean number of sales of cars over a 3-month period is 87, and the standard deviation is 5. The mean of the commissions is 5,225, and the standard deviation is 773. So say this is a car company or just a single car dealership, we don't know, but the average sales is 87 with a standard deviation of 5. So for the sales, I'll write it down here. The average is 87 and the standard deviation is 5. But for the commissions, which of course is going to be bigger numbers because that's how much they're getting paid. So the commissions, the average is 773. Whoops, wrong, sorry. The average is 5,225. And the standard deviation is 773. So if you look at those, you say, and somebody says, which one varies more? Well, that's kind of hard to tell because these numbers are so different. This is in number of cars. This is in dollars. These are fairly small numbers in comparison to these. It's really hard to tell. So if we compute the CVAR, the one with the biggest CVAR is going to be the one that's more variable. So the CVAR for this is just 87 over 5 and then switch it to a percentage. So 87 over 5 is 17.4, and so then if we I'm sorry, that was times. I should have divided 87 divided by 5. So it's 7, it's, is that right? Yeah, 17.4. Oh, okay, hold on. I messed up. What did I do wrong here, guys? I knew that 17.4 wasn't right.
7 over 5 instead of 5 over 87.
Yeah, I put the 87 on top. You're supposed to put the S on top, so that it's supposed to be 5 over 87. Sorry about that. So 5 over 87 is actually 0.057. If we change that to a percentage, that's 5.7%. So this has 5.7% for a C-bar. This one, do the same thing. Well, let's not make the mistake this time that I made. So 773 divided by 5225, you get 73 divided by 5225. This comes out to be about 14.8%. So which one's more variable? Commissions. Because 14.8% is bigger than 5.7%, so this is more variable. And again, all you're doing is you're comparing the standard deviation to what the average is. So this one has a bigger number in comparison to its average than this one has. The 5 compared to its average of 87 isn't as much as the 773 is compared to 5,225. Again, don't have to memorize it, just have to know how to analyze that. When you get a bigger number, that means that's the one that's more variable. And this could easily be that it's the sales. It's not because these are bigger numbers. If this one, if the you know, if the S, let's say, had been 10, then well, it'd have to be bigger than that. Let's say it was 15, then this would be bigger than that one was. So, okay, hold on one second. I've apparently got somebody at my door. So if I did 15 over 87, then that would be like almost 17%. I'll be right back. Okay, sorry, I had a utility guy at my door. Okay, so that is it for the last thing that they talk about in this section is what's known as the range rule of thumb. It's a quick and dirty way to kind of estimate the standard deviation, but I don't really ever want you to use that in any of our problems. So if they ask you something about it in homework, great, but I'm not going to ask you that on the test. So again, it's just a quick way to approximate the standard deviation. Okay, so let me kind of look ahead here a second and see what we've got left. Okay, so the last thing that we're going to talk about, not the last thing, the next last thing that we're going to talk about in section 3.2 is what's called Chebyshev's theorem. We've actually, chapter 3 and chapter 4 are kind of long. Just to kind of give you a heads up, we may be another 45 minutes before we're done with this. Maybe not, but this might go till like 12:45, 1 o'clock. But again, I want to keep going until we've covered it all so that you know, if you guys want to watch the video later, even if you have to leave, you can go back and watch the video later. I want all this information out there. So anyway, the next thing that we're going to talk about is called Chebyshev's theorem. And with Chebyshev's theorem, you have, I'm going to do the picture first. Thank you. It says that hold on. You have to quit. Lay down. Holy cow. All heck broke out at my house. My dog is not impressed with a strange person being in our backyard. Okay, so sorry. The cable guy showed up unannounced and needed into our backyard, and everything's going crazy here. All right, so Chebyshev's theorem states that if you have a set of data and you're looking at that set of data, that within a certain number of standard deviations, you should have a certain percentage. But this is really confusing because they haven't talked at all about what the standard deviations mean. So I'm going to start with that. So if you think of the average, okay, so let's do the car salesman. So the average car sales, the number of car sales in the month were, was it 87, I believe? Yeah, 87. So what we do is we put that average that's considered kind of our middle of our set of data. So the average number of car sales in that case were 87. I can't remember if they called it I can call that an X bar. They thought of that as a sample, okay? Then if I want to add standard deviations, remember the average was 87, and then it said that the standard deviation was 5. So if I want to add one standard deviation, that simply means that I'm going to take this 87 and I'm going to add 5 to it. So 87 plus 5 would be 92. Then if I want to add 2 standard deviations, I would just add another 5 to that, so that would be 97. Add another 5 to that, I have 102. And then if I added another 5 to that, I would have 107. And so if somebody said a certain data value was 4 standard deviations above average, in this case, 4 standard deviations above average would be a score of 107, or sales of 107. So a month that was 4 standard deviations above a typical month would have 107 sales. Does that kind of make sense? Does anybody have any questions on that? Hopefully somebody's still there. Is anybody still there?
Yes, it makes sense.
Makes sense? Okay. So then we're going to go this way. And this way we're going to have down 5, down 5, down 5, down 5. So this is considered -1 standard deviation. This is considered -2 standard deviations, -3 standard deviations, -4 standard deviations. And what this kind of cryptic thing is saying here is that from Chebyshev's theorem, at least 75% of the data should fall within 2 standard deviations. That's what Chebyshev's theorem says. And this was really big in the history of statistics when Chebyshev discovered this. He's basically saying that no matter what the data is, no matter how scattered out, how it's shaped or whatever, that if you go out 2 standard deviations, you should have at least 75% of the data. You could have more than that, but you have to have at least 75%. Then if you go out to 3 standard deviations, according to Chebyshev's theorem, you have to have at least 88.89% of the data. And then lastly, erase these for now. If you go out 4 standard deviations, you have to have at least, I'm going to put this slide up here really quick. This is actually the prior slide. And if you go out 4 standard deviations, you have to have at least 93.75% of the data. And that's really big to say that, 93.75% of the data, almost 94% of the data, should be within 4 standard deviations, that you really shouldn't see very much of the data that's beyond that. Now, when we get to chapter 6, I believe it is, yeah, chapter 6, we're going to learn what's called the empirical rule. They talk about it a tiny bit in this chapter, but I'm not going to harp on it very much. But the empirical rule is for data that is only bell-shaped. And bell-shaped for +1, +2, +3 standard deviations, you have 68%, 95%, and 99.7% of the data. So we get even bigger numbers if we can do a bell-shaped curve. Okay, but for right now, we're going to focus on Chebyshev's rule, which says that within ±2, you have 75%. Within ±3, you have 88.89%. Within ±4, you have 93.75%. Why do we not have ±1? Well, the answer is this is all derived from this formula right here. So you take, this is Chebyshev's actual theorem, is that any data set you'll have within K standard deviations, there'll be at least this much of the data. So where we get that 75% is we're within 2 standard deviations, ±2. You take 1 minus 1 over K squared. So this is 1 minus 1 over 2 squared. That's where that number comes from, because it's the 2. So 1 minus 1/4 gives us 3/4, which is 75%. That's where that comes from. This one is from the 3. And so we replace that 2 with a 3. And 1 minus 1 over 3 squared, or 1 minus 1/9, is 8/9, which is 88.89%. And then 1 minus 1 over 4 squared is 1 minus 1/16, which is 15/16. So if we tried to put a 1 in here, the reason that we don't have a number for 1 is because 1 minus 1 over 1 squared would be 1 minus 1, which is 0. So his theorem literally says that within 1% or 1 standard deviation up and down, there has to be at least 0% of the data. Well, that's not very useful to us. So we just don't really worry about that one because that one's not very helpful. So we don't do 1. We start with Chebyshev's theorem. We start with 2, 3, and 4. And you really kind of need to memorize these numbers for the test. Not like, I don't know how to explain it, like not like I'm not going to have you regurgitate 75%, 88.89%, but these might be choices that you have to pick from. So you have to kind of have in mind that ±2 is the 75, ±3 is the, almost 89, and the ±4 is the one that's over 90. Okay. Does anybody have any questions on that before we do an example of it? And I'll try to be more specific about how I could ask it on the test as we do the examples. But again, you notice Chebyshev's goes 2, 3, 4, whereas the empirical rule goes 1, 2, 3. So this is much stronger. It starts with 1 standard deviation, you're already at 68%, but that's only if we have bell-shaped data. So we'll come back and revisit that a bunch. Well, we'll completely talk about only those types of graphs in chapter 6, 7, and 8, or that kind of data in 6, 7, and 8. All right, so let's look at what this looks like in practice. Let's see if I can leave that there and post this next slide over here. Okay, so here it says the mean price of houses in a certain neighborhood is $50,000 and the standard deviation is 10,000. My word to the wise, my big, huge suggestion out of this is do not try to do this problem without drawing a picture. So draw a picture like we did before. Start with what the average is. So in this case, 50,000. That's your X bar. Okay, so this is your average. And then this 10,000 is your S. So if you mark 1, 2, 3, 4 standard deviations, that's going to be 60,000. I'm just going to leave the thousands off if you guys are okay with that. So 60,000, 70,000, 80,000, 90,000. Okay, these are all 1,000. This is your average. Then do it the other way. So this would be 40, 30, 20, 10. And so Chevyshev's theorem, it says find the price range for at least 75% of the houses will sell. Well, if you remember from over here, what was 75%? How many standard deviations?
Plus or minus 2.
Plus or minus 2. So you have a picture drawn, and if you've memorized that 75% is plus or minus 2 standard deviations, you just have to look at your data and say, okay, here's my middle. I'm going to go up 2, down 2. There's my numbers, between 30 and 70. So 75% of the houses will be between $30,000 to $70,000 selling price. They do it with this formula. I think that's confusing. Just draw the picture. Your brain likes a picture so much better. So draw this picture, figure out what they're asking. So if they had asked, 93.75% of the houses fall between what two values? You'd say, okay, well, 93.75%, that's plus or minus 4. So if I count, that would be 1, 2, 3, 4, 90,000 for my top number. 1, 2, 3, 4, 10,000 for my bottom number. And so 93.75% of the houses would fall between $10,000 to $90,000. And that's pretty much what I'm going to ask you on the test. If you can draw this picture and you know the percentages and you can count them out, you'll be fine. That's all you need to know. Anybody have any questions on that? There's an example, by the way, in D2L. I have an example of Chevyshev's theorem. It's like what's in the homework, though, not necessarily what's on the test. Because there's some in your homework that are just a little harder than what you'll see on the test. That one we just did is what you might see on the test, is one similar to that. If you can draw this picture and count them out, you'll be fine. Okay, so this next problem is a little bit more complicated because it doesn't fall right on one of those. So this is what you might see in your homework. A survey, so this is something you might see on the exam. This one you would only see on homework. Okay, so a survey of local companies found that the mean amount of travel allowance for executives was 25 cents per mile with a standard deviation of 2 cents. Stop, go no further, draw your picture. So what are we going to put right here in the middle?
$0.25.
25 cents, okay? And then we're going to go up and down. We're going to do 4 because we're talking about Chevyshev's. And what am I going to add to each of those and subtract?
0.02.
2 cents, okay? So 0.25, 0.27, 0.29, 0.31, 0.33. Don't even worry about what they're asking yet. Just draw your little scale here. Okay, so now what do they ask? Using Chebyshev's theorem, find the minimum percentage of the data values that would fall between 20 cents and 30 cents. Let me circle that with red. So 20 cents to 30 cents. Well, 20 cents is right here, and 30 cents is here. The problem with that is that's not on one of the ones that we drew, right? It's in between. So we have to use the formula. Remember, the formula is 1 minus 1 over k squared. This is minus 1 standard deviation, minus 2, minus 3, minus 4, plus 1, plus 2, plus 3, plus 4. So how far apart are 20 cents and 30 cents? How many standard deviations up and down is that?
Two.
It's more than 2 because 2 is 21 cents. We're down at 20 cents.
2.5.
2.5. And that's why this one is not going to be on the exam. It's only going to be on the homework because you actually have to plug this back into the formula and figure this out because it's 2.5. It doesn't fall on our nice 2, 3, 4 scale. Okay, so then this one is up 2.5, right? So that's our K. So K is 2.5. So the percentage is going to be 1 minus 1 over 2.5 squared, whatever that is. It comes out to be 84. So if you do 1 minus 1 over 2.5 squared, you'll get 0.84. So 84%, minimum of 84% between 20 cents to 30 cents. But you have to figure out how many of these you've gone up and down, and some of the ones on the homework won't be exactly 2, 3, 4. If they are, you already know the percentages for that. That's the 75, 88.89, 93.75. But it falls in between them like this. You've got to figure out how many it is, got to plug that in and compute it. Does anybody have any questions on Chebyshev's? There'll be one question for absolute certain about this on the exam, but it'll be like this one, okay? Okay, here's our picture of, let me clear all this out. So we're not really gonna talk about this right now much. They just bring it up really quick. In fact, I wish they wouldn't because I think it gets confusing with Chebyshev's. Hold on, I copied the wrong thing. But this is the empirical rule. But the empirical rule only works for data that's normally distributed. You notice this picture, it's all nice and even, and that's the 68, 95, 99% that we were, 99.7% that we were talking about. But again, this really isn't, we're really not going to focus on this. Focus on Chebyshev for now. We'll come back to the empirical rule when we get to chapter 6. Okay, we are done with the worst of the worst for chapter 3. We have a few little things we're going to finish up here with section 3.3. But we've done the hard stuff. The two hardest things in chapter 3 are calculating standard deviation and Chebyshev's rule. Now we're going to talk about measures of position, but these are really pretty easy stuff. This is the percentiles and the deciles and such. So measures of position are standard scores, percentiles, deciles, and quartiles. Now, standard scores are actually really, really important. And you guys, I know, have heard this in your lifetime. I'm absolutely positive you've probably been told more times than you want what you scored on some standardized test. Okay? So a standardized test is a test where they use standard deviations to tell you how well you did. Okay, so let me kind of mark these. So standardized test is where they tell you how good or how bad you did using standard deviation to compare to the rest of the data. Percentiles, they compare you to a typical 100 of the data values. So they say if they're giving you a percentile, they'll say you scored at the 87th percentile, that means you scored better than 86 out of a typical 100 students did. Deciles is just like percentiles, but they use 10. And quartiles is they use 4 or they split into quarters, like we were doing with the Q1 and the Q3. So this, they split it into quarters. So let's do some comparisons. So if somebody said you were at the 50th percentile, that's the same thing as if you were at the 5th decile, which is the same as if you were at Q2, which is the median. Those all mean the same thing. So the middle of a percentile would be the 50th percentile, the middle of a decile would be the 5th decile, and the middle of quartiles would be Q2, which is the median. They all mean the same thing. So they all mean, and then if you're talking about standard deviations, it'd be your 0 standard deviations. So 0 standard deviations, 50th percentile, 5th decile, and median or Q2 are all the middle of a set of data. And so let's look at how you calculate a standard score. It's really quick, and but this is kind of important because we're going to come back to it. Right now, we're just going to calculate these standard scores, but when we get to chapter 6, we'll be doing a lot with it. So it's really nice to know this and practice it a little bit now. So let's say, ooh, I'm going to do this without, oops, that's not what I wanted to do. Okay, so I'm going to try to put this up on the screen without giving you the answers here because it's such a quick calculation that I think people miss what we're doing. So here's the problem, but I took away the rest of the slide so you can't see it. So let's say a student had a 65 on a calculus test that had a mean of 50 and a standard deviation of 10. And then she had another test with a different average and a different standard deviation. Compare the positions of the two tests. So let's look at this first one. So here's her first test. In order to get her Z-score, you're going to take her score, we're going to subtract the average, and then we're going to divide by the standard deviation. You could do it with populations, but we typically do that with a sample. That's why we have the X bar and the S instead of the mu and the sigma. Okay, so her score, what was her score on this test?
65.
65. What was the class average?
50.
50. And then the standard deviation is 10. So she scored 15 above average when the average on the test is 10. So if we were going to draw a scale for this, see if I can get rid of some of this other junk up here. So if we were going to make a scale for this, what we're saying is she, the average score was 50 and she scored up at 65. Where is that at, is what we're saying. Okay, so this is 1.5. So what we're saying here is she is 1.5 standard deviations above the average for that test in that class. So if we went up here, let me erase the 6.5 and or the 65, and let's do like we were doing with the other things. So if we said 10 standard deviations, remember the average was 50, we're due 10 is our standard deviations. So this would be 60, 70, 80, plus 1, plus 2, plus 3. She scored, with her 65, she scored right here. So she was more than 1 standard deviation, but not 2 standard deviations. In fact, she was right in between them. She was plus 1.5 standard deviations above average. That's what that Z-score does. So for that test, she was 1.5 standard deviations above the average class, or average student in the class, I should say. Anybody have any questions on that one? So it's a real quick calculation, just score minus average divided by standard deviation. Okay, so let's try this one really quick. She scored a 30 on a history test that had a mean of 25 and a standard deviation of 5. So her Z-score for that test, her score, her X, was 30. So still above average because the average was 25. Standard deviation was 5. So she scored 5 points above average on a test where a standard deviation was 5. So she scored 1 standard deviation above average. I'll just say it's 1. So her Z-score on this one is 1. So if we were to make a scale for this, the average was 25, and the standard deviations are 5s, and she scored right here. She scored a 30. She's solid 1 standard deviation above the average score. Does anybody have any questions on that? Okay, so which one did she do better in comparison to the rest of the class? Did she do better on her calculus test or on her history test in comparison to the rest of the class?
Calculus.
Calculus, yeah. So she, but it's hard to tell when they have different averages and different standard deviations. What we just did is we standardized it, and we said, let's not talk about points and standard deviations. Let's talk about how many standard deviations. So it basically takes this and thinks of it like 0 standard deviations, and then it counts it up. That's called standardizing it. So we just standardized her score. That's what they do on standardized tests. Okay, so like I said, we just got a couple real quick things here. We got to talk about percentiles. In order to calculate a percentile, oh, why did it not copy that? There we go. In order to talk about a percentile, you're going to separate the data into 100 equal groups, and to get the percentile rank, you take the number of values that are below a certain value, add 0.5, and divide by the total. And then to get your placement, which is the C, you're going to take N times P over 100. So let's look at what that means. I don't like that graph. We're not even going to look at it. So here's an example of the first thing. So if you had a teacher that gave a 20-point test to 10 students, find the percentile rank of a score of 12. First of all, just a note, this is very strange. You normally wouldn't take less than 100 people and be talking about percentiles. Typically, when we're talking about percentiles, you're talking about more than 100 people. So you're talking about like thousands of people taking this test, and you're trying to break it down to see where you would fall in a typical 100 people. So this is really a weird problem because they're starting with 10 students and then going to percentiles, which is odd. But anyway, we'll go with it. So we have the scores in order. So we have to put them in order first. And we want to find the percentile rank of, did I skip something? Nope, I did not. Okay, so we want to find the percentile rank of the score of 12. So we're looking at this score right here. So to compute that, to get the percentile, you're going to take the number of scores that are below 12. So 1, 2, 3, 4, 5, 6 scores that are below 12. That's where they got that 6 from. Then you're going to add 0.5, and then you're going to divide by the total number. So it said that there were 10 students, so we're going to divide by 10. And that'll give us our percentile. So the percentile rank for that student, he's at the 65th percentile within the class. Better than average, not the top of the top, 65th percentile. Any questions on that one? Okay. This next one is a little counterintuitive. This is how you use that other formula. So what if they ask you, instead of what's a certain score's percentile rank, what if instead they ask you to find a certain percentile? So in this case, it says find out of these scores, find the person who's at the 25th percentile. So what we do for this, these variables are kind of hard to understand. The n is the same as it was up there. So that's the number of scores. So in this case, that's the 10. The P is the percentile rank that you want. So because we want the 25th percentile, we're going to use a 25 because they wanted the 25th percentile. Okay, and then the 100, you always use a 100. So in this case, we're going to get our C, we're going to take 10 times 25 over 100, which gives us 2.5, which we're going to round up to 3. So you look at this and you say, oh, okay, I got a score, I got 3. So my answer must be this student right here that got a 3. No. What this means is it's going to tell you the rank, like the score in order. So this doesn't mean a score of 3. So this is not a score of 3. It's the third score. So that 3 means the third score. So I go over here and I count 1, 2, 3. The 5 is the 25th percentile. So I wish they wouldn't have had a 3 as one of the scores. It would have made it easier. Here, let's pretend that 3 didn't even exist. Say it was 2, 4, 5, 6, 8. So that person right there is the 25th percentile because they're the third score, according to this formula. Little weird. Definitely neither of these will be on the test. Let me put that here. Homework only. There won't be anything about percentiles on the test. Okay, and then deciles. So deciles, like I said, they separate the data into 10 equal groups. So a decile of 1 is the same as a percentile of 10. Decile of 4 is a percentile of 40. Quartiles, a Q1 is like a percentile of 25. A Q2 is like the median. A Q3 is like a percentile of 75. And then the interquartile range is found by subtracting whatever you get for Q3 and Q4. Oh, I lied. We do cover 3, 4. It's 3, 4 is pretty much, I don't know why they made it its own chapter or its own section. Okay, so we already talked about these quartiles a little bit, so hopefully this will be very painless. So it says here, find Q1, Q2, Q3 for this data set. And so to do that, we put them in order. So 5, 6, 12, 13, 15, 18, 22, and 50. And so in order to find those, remember that Q2 is the median. So we're going to start with the median. So the median is here. And so the median, which is the Q2, is 14. Are you guys okay with where I got that? Just halfway between 13 and 15?
Yes.
Good. Okay. So now we need to do the Q2 and the Q3, which are halfway on either end. So the Q1 is in between 6 and 12, and the Q3, remember, think of them like quarters, into the first quarter, halftime, into the third quarter. And so Q1 is the average of 6 and 12, which would be 9. And Q3 is the average between 18 and 22, which would be 20. You don't have to do those in your head. Just 6 plus 12 divided by 2, 18 plus 22 divided by 2. Those ones just happen to be nice enough numbers to do in my head. So those are the Q1, the Q2, or the median, and the Q3. And what we're going to do now is we're going to use those to do a box plot. Before we do that, we're going to talk about outliers really quick. So this is the formula for outliers. And an outlier is considered an extremely high or low value. And in order to do that, you would take, so let's see if this data set has any outliers. So in order to find the outlier, you're going to take Q1 minus 1.5 times the interquartile range. So in this case, Q1 would be 9. Then you're going to subtract 1.5 times the interquartile range and see what value you get. The interquartile range is how far it is from here to here. So the interquartile range for this data set is 20 minus 9, which is 11. So interquartile, between the quartiles. Inter means between. So between the quartile ranges. So between the Q1 and the Q3, it's 11 apart. And that actually gives us a negative number. So we get negative 9 minus 1.5 times 11 gets us negative 7.5. So do we have any data values that are as low as negative 7.5? Well, of course not. We don't even have any that are in the negatives. So no outlier, call it a low outlier. So there's no low outlier. And then we do the exact same thing, but in the other direction to see if there's an upper outlier. So Q3 is 20. Let me do it with a different color, kind of color code this. Use obnoxious orange here. Okay, so we're going to use Q3, which is 20, and we're going to add 1.5 times the interquartile range. That gives us 20 plus 1.5 times 11 gives us 36.5. So are there any upper outliers in this data set? Are there any values that are 36.5 or higher?
Yes. 50.
Was there a 50? There was a 50. I had it hidden there. I almost fooled myself. So you are correct. So in this case, that 50, because it's, oh, my pen again. Okay, so because 50 is above 36.5, that's an outlier. So you're correct. You analyzed it right. So the 50 would be an outlier because it's above 36.5. And that's how we check for outliers. So this data set has one outlier, and it's that upper number, that 50. And it's, in general, it's just a number that it lies quite a bit above the regular data. And if you look at this, 5, 6, 12, 13, 15, 18, 22, 50, we jumped, 28 value points between the last two values. Okay, so now we're going to make a box plot, and we will officially be done. Hey, I was pretty good at guessing that. I said 12:45 to 1 o'clock, and we got 12:48 right now. So this will take us about 5 minutes, and we'll be done. Okay, so in order to do a box plot, we need what's called the 5-number summary, which sounds all big and special, but all it is the quartiles plus the highest and lowest value. So put this right here. So for this data set, the 5-number summary is, for this data set, the low is 5. Let's do that different. So the low equals 5. Sometimes that's called the minimum. Q1 is 9. The median is 14. Remember that from right there. The Q3 is 20. And then the high or the max, I'm going to put that here. So min or low, max or high is 50. That's that one that was that outlier. That's called the 5-number summary. It's got this big fancy special name. Just the low, the high, and the 3 quartiles. And with that, we can make what's called a box plot. And the box plot is just this kind of cool little graph that we can make that includes these things and kind of gives a pictorial view of how things are spread out in the data set. So in order to make it, I've got to have on my scale here, I've got to be as low as 5 and as high as 50. I've got to be able to span all of that. So I think what I'm going to do is I'm going to start at 0, and I'm just going to go by 10s. So 10, and this is up to you if you're doing it on your own. So 30, 40, 50. Okay, I got a bunch of extra up here we'll get rid of. Okay, so there's my scale. Maybe I'll even go back in here and make little marks halfway so I can kind of see it, even though I'm not going to write the numbers in. So there would be 5, 15, 25, 35, 45. And I'm going to see if I can color code this again. The first thing I'm going to do is I'm going to put where the median is. And I'm going to put it with a little line. So my median is right here. That's a little bit too far over. So I want it right above 14. So more like there. Okay. Then I'm going to do the same thing for the Q1 and the Q3. So Q1 is at 9. Q3 is at 20. And this box is in the interquartile range. So you put a little box around your interquartile range. Then you go and you do your low and your high with just a dot. So your low is at 5, your high is at 50. And you put little, it used to be called a box and whisker plot when I learned it. Now they tend to just call it a box plot. So this is like your box and this is your whiskers. So you can see this data is pretty close together in the bottom 25%. A little bit more spread out between the next 25 and the next 25%, and then really spread out in the top 25% because we have that outlier. So it's really spread out from Q3 up to the maximum, and that's called a box plot. So obviously if you're doing it in the homework, it's not going to have all these beautiful colors, but it will just look like this. And so you might be asked on your homework or on the test, what say it said 25% of the data fall above what? Well, you would say 25% of the data fall above 20 because that's your Q3. Remember, this is 25% of the data, the next 25% of the data, the next 25% of the data, and the remaining 25% of the data. So 25% fall above 20, 75% fall below 20, half fall above the median, half fall below the median. So it splits it up into quarters. That's all I have unless you have a question. That's everything. I know that's a lot for one day. I would highly recommend you go do your homework for chapter 3 before Thursday. Get it out of the way. Because we cover a lot of stuff this week. But does anybody have any last minute stuff before we go? Okay. Have a great day. I will see everybody that can make it on Thursday. And like I said, my recommendation would be to do your homework. You're very welcome. You're very welcome.
Thank you. I appreciate it.
Thank you. I'm glad a couple of you were able to stay anyway. I appreciate you guys being there. And
Thank you for being willing to keep going.
well, otherwise I'm just going to people are just going to be super confused. So it's better to just stick it out and get it done and have it available to people. Have a great couple days. We'll see you guys back on Thursday.
Thank you so much.
Bye.
Bye.